So the next video in our series is on bubble sort. So bubble sort, just like the other n-squared algorithms, usually keeps a subset of the array that's unsorted and a subset of the array that's sorted. So here, our little pseudocode algorithm says we're again going to go from the end of the array to the front, and every time we're going to bubble the correct element. So we're going to swap anything that's out of place, right? So if we find two elements next to each other that are in the wrong order, we're going to flip them. And we're going to do that as many times as there are elements in the array. What that essentially does, right, is it takes the maximum element and it puts it at the very end of our unsorted part of our list. But it does that by swapping only neighbors, right? So instead of going through and finding the max, as it's going through, it's actually finding subsections that are sorted incorrectly. So let's see how that works real quick. So the first thing it does is it takes this 15 and the 7, and it says, well, those are in the wrong order, so I'm going to end up swapping 15 and 7. And then 15 and 3 are in the wrong order, so I'm going to swap 15 and 3. I'm going to swap 15 and 8, right? So you can see 15 has made its way from here to there, to there, to there, and it started to sort of bubble up to the top. But then we get to the next guy, 15 and 18. Well, they're in the right order, so we're not going to do anything. But then we look at 18 and 12. Those need to be swapped, and pseudo 18 and 2. And now 18 is the maximum. So after the first round of bubbling, our array, the sorted part of our array, right, looks exactly like the sorted part of selection sort, right? After one iteration, they look very similar. The one thing that's different now, though, is that the higher numbered things are closer to this end and the lower numbered things are closer to that end, right? Because before we would have swapped 2 and put it here, and 15 would still be all the way at the beginning. So the next thing is to look at 7 and 3. So now we start over and we start bubbling from the beginning again. 7 and 3 are going to swap. Well, 7 and 8 are already in the right place. 8 and 15 are already in the right place. But then 15 and 12 need to swap. So you can see if you're looking ahead, 15 is going to go from here to there, right? And that's exactly what happens. And now, again, at the end of 2 rounds of bubbling, the sorted portion of our array, which is just these 2 elements, looks exactly like the sorted portion of the array for selection sort. But again, it's the unsorted section, right? All of these things that are different than they were in selection sort. So again, we do bubbling. 7 and 3 are in the right order. 7 and 8 are in the right order. 8 and 12 are in the right order. And really what's going to happen is this 2 and 12 are going to swap, right? So 2 is going to go there. And now, again, that's the same that it was before. And we keep doing that, and we see that this whole thing is already in order. We're just going to have to sort of get 2 back to the beginning. And when we get here, we run the swap again, and once again, 2 is in the right place. So just like we did with selection sort, we don't actually need to go all the way. So here we have our I going from the end of the array to the beginning. We don't actually have to go that far. We can go to I greater than 0. Right? Does it make a difference if we leave it as I greater than or equal to 0? Well, it depends on our implementation later on to make sure we don't have an out of bounds error, but probably not, right? So speaking of which, let's look at the code real quick. We can see, once again, we have this I going from the end of the array to the beginning. And really all that's doing is, right, because I doesn't really come into play here other than how far we go with the bubbling. But then it says basically go from 0 to I, and we're going to check every pair of elements, j and j plus 1, and swap them if they're in the wrong order. Again, swapping takes a constant amount of time, but it's 3 operations, right? So then the question is, what's the running time? Well, this inner guy, right? The running time, this for loop runs, it goes from 0 to I. So its running time is O of I. And we know that this outer guy runs O of n times. So that leaves us with our good friend, the sum of I from 0 to n, which is O of n squared. Right. And this is the worst case running time. So one of the things they discussed in the book that we didn't actually discuss in class is that you can do a little bit better with bubble sort, right? If you're given, say, a sorted array already, bubble sort can go through and basically it won't ever have to swap anything. And it knows that. So what we can do is add a little bit of a short circuit, right? Let me see if I can clear all this out real quick. So we can add a short circuit to this code. And we can say up here, let's add Boolean swapped. And initially we set that to true. And in this condition we want to say I not only greater than 0, but and swapped. And then in here, we're going to insert swapped equals false. And in here, we add a swapped equals true. So what does that do for us? Well, so initially swapped is equal to true, so we're going to run this loop at least once, right? So we have our array, and we have our little guy that runs across it once. But if in here, right, so if we made a swap, if we needed to swap two things, even if they're in the middle, then the flag, right, this flag gets set to true, and we run the loop again. But if there's a case, where we make an entire iteration and we don't do anything, what does that mean? Well, that means that everything was in the right order already, and we can stop. So in that step, really what it is you're verifying that everything that's left is already sorted. So this is similar to in the homework, right? Our isSorted method for our linked list basically just verifies that everything is sorted. So if we make a pass where all we're doing is verifying that things are sorted, then we can stop. Which means the best case would be if assuming we implemented these changes, right? If we implemented these changes and I gave you a sorted array, what's the running time? Well, the running time is just order n, right? Because all you have to do is make one pass where you verify everything is sorted and you're done, right? So in this case, the worst case running time we know is order n squared, but the best is order n, right? Okay, the next video is going to be about merge sort, and I will be posting that shortly.